In this talk, I will be covering many aspects of cosmology and time. I hope you have many questions, and to help identify whereabouts in the presentation we are when your question arises, I have put in a slide number in the bottom left-hand corner. I would like to demonstrate that something about time can be considered a fundamental property of the universe and a solution to many of the problems that beset current cosmological models. I draw much of my inspiration from Einstein's relativity theories, yet challenge some of his conceptual ideas. In this presentation, I would like to explain why I think that time dilation does not just occur when an object travels fast, or approaches a massive object like a planet, but that time also has a hidden dimensionless parameter where time dilates over time, making time faster in the past and slower in the future. This can validate our notion of an arrow of time. I will explain why time dilation is accompanied by matter dilation, shrinking not just our objects but also our light speed measuring rods relative to the past. Our ruler shrinking is why we think the universe is expanding and that the apparent recessional velocity of distant galaxies is a fictitious movement where the measured distance is changing, not the actual position. I'm proposing that the Big Bang never stopped, where our infinite universe is just one of infinitely many separated by their infinity and time dimension, each universe being part of a fractal loop, where matter and antimatter separate at birth, each one initially forming their own infinite ball of plasma that, after an aeon of time, all matter will end in infinitely many black holes before cycling back to the singularity. Gravity is part of a similar, self-similar distance asymmetry feedback loop. Welcome to this presentation about time, but not time as you know it. Time and distance are inextricably linked due to the apparent immutability of the speed of light, and this is how that story starts. Take this ringing alarm clock and take the air out of the vacuum jar, and the sound has no medium through which to travel, and so physicists would ponder, what was the elusive medium left through which the light is able to travel? Through most of the 19th century the answer was the luminiferous ether, but what that was, and how to detect it, were two of the burning questions of the time. Luminiferous just means that it is something that is able to support the propagation of light. In 1887, two proponents of the ether theory, Michelson and Morley, set up an experiment to see if the Earth's 67,000 mile-an-hour movement around the Sun had an effect on the speed of light. With a state-of-the-art Michelson interferometer, at the time the most expensive scientific instrument ever constructed, set about the task of detecting the Earth's motion through the ether. Imagine the Earth and the instrument moving in this direction. The device spits light and sends it off into two different directions before recombining it. Any difference in the speed of light due to this movement would be detected as the light would return out of phase. But what they found was no difference, and no result that set in motion a paradigm shift in our scientific understanding. Lorentz and Fitzgerald concluded that the only way this could be the case was that the instrument and all moving objects must shrink in the direction of their travel. Evaluating patents was a good exercise for this future physicist. The genius of Einstein and his relativity theories is in the way that he uniquely understood many of the ideas of the time and amalgamated them in with his own thoughts. Einstein's laboratory was his mind, where he would often run thought experiments, travelling with electrical signals or racing through space on a beam of light. With his anomalous mind, he was able to see within Maxwell's equations something unnoticed by Maxwell himself, that light travelled at a constant velocity, whether travelling on a train or a comet. A recondite thought led him to realize if all observers were to agree with this notion, then time itself would have to beat at different rates for different observers. The faster one moves, the slower time will progress. Think of it this way. Alice here has a clock that is regulated by a photon bouncing between two mirrors. If we give an identical clock to Bob and get him to put into motion relative to Alice, the photon in Bob's moving clock has further to travel and so ticks slower. Now when Bob passes Alice, Alice will see Bob's clock run more slowly. The mathematician Hermann Minkowski saw that special relativity could be described with non-Euclidean space-time geometry, where the three spatial dimensions, shown here as 2, are augmented by one of time. Of course, the light cone diagram could be put at any angle. I always think of it as this way up, as we get past light from the stars above. Well, actually, all the light that we see has reached us from the past. With a mutable light speed, space and time are one, and so distances can be measured in time intervals, for instance, light seconds. And imagine Bob here overtaking Alice. His clock will be running slower, and so experiences fewer seconds. His length will be contracted due to the Lorentz Fitzgerald length contraction, and, according to Einstein's special theory of relativity, the space through which he is travelling will also be contracted. This way, both Bob and Alice agree on the speed of light. Einstein's theory of special relativity had sown the seeds for a revolution in physics. Knowing that space and time were not the immutable absolutes on which Newton had based his theories, Einstein knew that the mechanics of the celestial bodies, in other words gravity, would have to bend to the will of the new space-time geometry. Challenging Newton's most successful theory of all time would be a bold move indeed, and his old friend Max Planck, founder of quantum theory, warned him, "As an old friend, I must advise you against it, for in the first place you will not succeed, and if you succeed, no one will believe you." The mathematics involved would become very challenging for the young Einstein, and it would take a further 10 years before publishing his general theory of relativity, which underpins modern cosmology. When we look at a star in our galaxy and analyze the light by splitting up the frequencies, we normally do this with a diffraction grating. We notice that there are a few dark lines in the spectrum. Atoms absorb light. Different atoms absorb different wavelengths, and so atoms in the outer layers of the star absorb some of the light, giving the star a kind of fingerprint, which is better seen when we turn it into a spectrograph. When we look at a distant galaxy, it may not come as a surprise to find a similar pattern, as the light from a galaxy is emitted by just a whole load of stars. When we match up distinguishing features like these two troughs, we notice that they do not line up. It is as if the pattern produced by the galaxy has been shifted, in this case, towards the red end of the spectrum. The redshift is the difference between them. If shifted the other way, we have a blue shift. The first indication that the universe was expanding came when Vesto Slipher was charged with the job of obtaining spectrographs of spiral nebulae. We now call these galaxies, but at the time we did not know anything lay outside of our Milky Way. He noticed that the spiral nebulae had a spectrograph very similar to starlight, indicating that they were made of stars and so a very long way off, unlike planetary nebulae. He also noticed the spectrographs were shifted and assumed that this was a Doppler shift, and that the nebulae were moving, and that the Andromeda nebulae, having a blue shift, was indicating an incredible velocity of 300 kilometers per second, towards us. Turning the astrograph around, he found that most spirals were redshifted and so moving away. This challenged the belief that the Milky Way was all that existed. When Einstein published his general theory of relativity, the leading astronomers assured him that the universe was static, which meant that his elegant field equations had the same problem that beset Newton. Soon after, Sir Isaac Newton had published Principia in a letter to the Reverend Richard Bentley. He had posed the question: since gravity is always attractive and never repulsive, then any collection of stars would naturally collapse in onto themselves. He argued that a finite collection of stars would end up as one fiery superstar. He also pointed out that if the universe were infinite, then the collective force in every direction would pull all the stars apart. He could only presume that God made constant, minute adjustments, but Einstein was forced to put in an ad hoc parameter that he called the cosmological constant. However, in 1922, Alexander Friedmann simplified Einstein's equations by assuming that the universe was homogeneous and isotropic at a large enough scale. In other words, it looks and behaves the same everywhere if you take a big enough sample. This is known as the cosmological principle. He then found a solution to Bentley's paradox by saying that the universe is expanding. His paper was largely overlooked at the time. Another paper, largely overlooked at the time, came from a Belgian priest who had studied particle physics. He is considered the father of the Big Bang cosmology, known then as his fireworks theory. Unaware of Friedmann's earlier paper, he had predicted an expanding universe where distant galaxies would be racing away at an ever-increasing velocity, with a velocity-distance relationship. He came to the logical conclusion that if everything is racing away now, then if you run the clock backwards in time, everything was closer in the past. He predicted that the universe had emerged from a primordial atom that created the universe from a cataclysmic cosmic event from a finite point in space and time. It would be many years before Einstein accepted that the universe was expanding, with the conclusion that his cosmological constant was his biggest ever blunder. For many thinkers, time having a beginning is still problematic. In 1929, using the world's largest telescope at the time, Hubble's observations of nebulae redshifts, along with their estimated distances, reveals the linear distance-velocity relationship that we now call the Hubble constant. Hubble was unaware of Lemaitre's theory, but both had assumed that this redshift was a Doppler effect and considered that they had a real kinematic movement through space, unlike today where we consider that it is the space between the galaxies and clusters that is expanding that causes them to move apart. Many thought that the creation of the universe via an explosion event implausible, such as Fred Hoyle, who pejoratively gave the name Big Bang to the theory, and the name has endured ever since. At the time, most in the profession favoured Fred Hoyle's steady-state theory. Then, in 1964, Arno Penzias and Robert Wilson rather serendipitously discovered the cosmic microwave background radiation. First predicted in 1948 by Alpha and Herman, this first light has undergone a redshift from 2 micrometers to 2 millimeters and is sometimes described as the afterglow of the Big Bang. And so, the Big Bang solution was, until 1998, an expanding space due entirely to a cataclysmic explosion event that created the universe. It explained why we see this Doppler redshift in distant galaxies, and why the universe has not collapsed in on itself. The energy from an explosion event cannot, on its own, keep the universe expanding forever. The collective force of gravity or space-time curvature should be slowing down the expansion. and so to further validate the Big Bang model, an effort was made to detect the slowdown to the expansion by observing type 1a supernova explosions. These always explode with the same brightness, so they can therefore act as a standard candle. Their brightness is relative to their distance. What they found was not at all what they expected to find. The expansion of the universe was speeding up. This unexpected result, considered by some to be a falsifiable test for the Big Bang model, would lead proponents to rescue it by resurrecting Einstein's ad hoc cosmological constant, albeit with a different value, and now often referred to as the mysterious dark energy that pervades the universe. I had expected this discovery to usher in new cosmological models, but none have so far usurped the Big Bang. I have my own theory that I call the fractal topology of space-time theory. In this theory, matter shrinks and time dilates over time, making much of what we believe to be a constant, like the fine structure constant and the constant speed of light, actually variable over time, and where the expansion of space is only a fictitious movement of distant objects as our light speed measuring rods shrink. The whole of time cycles in a fractal loop continuum, because the Big Bang, or Genesis moment, has never stopped. I have since discovered that some of my ideas already exist, like the cyclic eons of time in Sir Roger Penrose's conformal cyclic cosmology, popularized in his book Cycles of Time. In his lectures he uses this painting by Maurice Escher, modelled on the mathematics of a Poincaré disk, and as he said, named after Beltrami, who formulated the model. There is also Olivier's self-similar model of the universe, where evanescing matter and the Hubble parameter is keeping some of the constants constant. I also found an article in New Scientist that explained a theory where time is slowing down, proposed by Professor Jose Senavilla, and then there is E-infinity theory, where space and time has a fractal topology proposed by the controversial Professor L. Nashji. An Escher painting has been used in describing this theory. But in the fractal topology of space-time, I would have to invert the Poincaré disk, a bit like this dynamic fractal pattern. El Nashdi commented on one of my YouTube videos, all but accusing me of plagiarism. I had to look him up to see how similar my theory was, pleased with the similarities and assured by the differences, and so replied, thanking him for his comments and pointing out my amateur status and how I found his implied charge a compliment coming from such an esteemed professor. He did not answer, except for with a like. I use thought experiments like this to deduce my ideas. Here we have Bob in his spacecraft. If he is travelling at great speed, as he approaches an observer, the light from him will appear shifted towards the blue, and shifted towards the red when moving away from an observer. He will shrink in the direction of travel with the Lorentz Fitzgerald length contraction. Special relativity says that space he is travelling through also contracts, and time dilates, slowing his clock. But does that mean that in his past, distances were longer, time faster, and was he expanded like this? Or that in the present he has a strange, non-conformal, asymmetric distortion? The problem is this interface, right here. I recall Simon Schaefer on a BBC programme reflecting on the paradox of time, and basically what he was saying was that the past no longer exists, like Lonesome George, the last of his species who died not long back. There is evidence that he did exist, but he's stuffed and on display in a museum. We can make predictions about the future, but that does not yet exist, and its chaotic emergence is in the present. How wide is this present? If it is just an interface, that too does not exist. And as a presentist, I believe that our present must be infinite and unbounded. We think of the arrow of time as a direction through which we travel, and our theories insist that time can also go backwards, no matter how unlikely, although no confirmation of this has ever appeared. We often think of a movement as travelling along a timeline, one temporal dimension and three of space. I think of time as three-dimensional as the objects that exist in time. As Richard Feynman once said, time is what carries on when everything else is stationary. So if Bob here is stationary or moving, he will still travel through time. General relativity informs us that proper time at the top of a building will be that bit faster than on the bottom. This gravitational time dilation effect can actually be measured if you have two modern atomic clocks. This cesium atomic clock is the sort of device that is used in GPS satellites and cost about £1,000. You may think time will run faster at the Hubble Space Telescope, it being about 370 miles above the Earth, but that is not that far, and its 97-minute orbit will mean that it is travelling at 17,500 miles per hour. This means that the time dilation due to special relativity makes time there slower in its low Earth orbit than time on Earth. Satellites used by our in-car navigation devices fly much further out where the orbital speed is slower and gravity weaker, and there time does run faster. Higher up still, we have the geostationary equatorial orbit, where satellites fly 2.5 times slower than the Hubble Space Telescope, such as this Syncon 3 at 22,25 miles up. It remains above the same spot on the equator. In a thought experiment, you can imagine it at the top of a ridiculously high building, or on the end of a space elevator, first conceived by this chap in 1895. Because time runs faster at the top of the elevator, travelling there, you would experience an extra 45 nanoseconds of elapsed time. With the speed of light measured the same everywhere, on the space elevator you can see that at the top light has longer to travel during one sidereal day than at the base on terra firma, an extra 44 feet 2 inches. And so light there is relatively faster, even though it has the same measure. It has a faster coordinate light speed at the top relative to the base. The length of a ruler is defined by the elapsed proper time a photon takes to transit a ruler, and time is atomic, based on properties of a cesium-133 atom. So if the speed of light is relatively faster at the top of the space elevator, then a ruler there will be relatively longer than one at the base of the space elevator. This will result in a distance asymmetry where the distance from the top of the space elevator to the Earth and back is shorter than the distance from the Earth to the top of the space elevator and back. It is the same cable, but at any one moment the absolute displacement of space between the base and the top of the elevator will have a proper measurement which is dependent on the observer's position on the cable and consequently their level of time dilation. The top and the bottom of the elevator have displaced the same cosmic time, but at different proper time rates. Descending the elevator changes the scale of your measuring rods, and so the proper distance to a very distant galaxy will increase as you descend the elevator. Let's go back up for the next slide. If we are to consider that time dilation will shrink your measuring rods, then the recessional velocity of distant objects could be due to changing time dilation. I'm hereby proposing that time dilating over time is a hidden, non-local parameter that keeps the constants only apparently constant and relative to the atoms of the observer, and a fundamental property of time in the universe. Where time dilation shrinks the rulers, then the atoms that the rulers are made of are also smaller. And if time is dilating over time, then everything in the universe that is made of atoms will also be shrinking over time. The redshift that invokes the recessional velocity may not be a Doppler shift at all, but more akin to a gravitational redshift due to the atoms of the distant objects being larger when the light left relative to now. The changing distance is therefore a fictitious movement that requires no energy to invoke it, a changing distance relative to the time dilation of the observer. So as Bob flies past, he will be shrinking, but not just in the direction of his travel. So if things are shrinking anyway, then contraction is just one aspect of an isomorphic transformation that all atoms are undergoing. They just shrink quicker for Bob as his proper time is running slower. In this famous thought experiment for time dilation that is known as the twins paradox, when Bob here travels at relativistic velocity, there is nothing special about his shrinkage, only the duration of his absence relative to his twin. In Bob's moving frame of reference, time is running slower than it is on Earth for the time displacement of his journey. Bob and Alice displace absolute cosmic time moment by moment with synchronicity. Newton may have called these moments fluxions and Leibniz infinitesimals, but Bob experiences less elapsed proper time, and so as he was travelling, the redshift of distant galaxies would be changing quicker, and so I am thinking that Bob would have to measure a faster Hubble constant, and so the Hubble constant is therefore an indication of the changing time dilation of the observer. The absolute way in which cosmic time is displaced simultaneously can, in principle, unify the two theories of Einstein's relativity. Cosmic time is a dimensionless parameter, and so no age or absolute time increment can be inferred from a cosmic time infinitesimal. Only the order of events. Proper time is relative in a scalar way that keeps that chronological order. As John Wheeler once said, time is what stops everything from happening at once. Remember how, when Bob passes Alice, and Alice saw Bob's clock run more slowly? Well, Einstein had to concede that Bob can also consider himself stationary and that it is Alice that is moving, and so her clock is slower. This counterintuitive idea that time can be slower for both Bob and Alice at the same time need no longer apply now that proper time is always dilating, so as cosmic time can be maintained in an absolute chronological order. Current theories put the recessional velocity down to the space between the galaxies and the galaxy clusters stretching. An analogy for this is to sew buttons on a piece of elastic to represent the galaxies and pull the elastic apart like this. The buttons move apart but remain fixed to the same spot on the elastic. The galaxies move with space and not through space. By designating the left-hand button as the observer, we can see that the further away a distant galaxy is in relation to the observer, the faster that its recessional velocity will be. An observer in a different galaxy would also see every distant galaxy moving away from them. Creating space this way is an ad hoc solution that I think defies the laws of thermodynamics. In the fractal topology of space-time theory, it is a rather subtle difference, as no space is being created, yet both galaxies would see the other as getting further away, as if it were due to distances being peculiar to the observer. The observer on the left would think that all the galaxies here are moving away with a distance-velocity relationship, where it is really a manifestation of their changing time dilation. The relative distances are changing, but the position of any galaxy is not. The position in space and time for any distant object will be in the same order for any observer at the now moment, although the numerical time or distance value may differ depending on the time dilation of any particular observer. Imagine we are inside this red circle, and this is a megaparsec, a distance that light travels over a period of nearly 3,300,000 years, travelling at 186,000 miles per second, and so that's pretty far out. Here, galaxies are moving away with apparent recessional velocity of about 70 kilometers per second, and twice that velocity at 2 megaparsec, and so on and so forth, with a linear progression. The constant increase in velocity over distance is therefore 70 kilometers per second per megaparsec, and this is what we call the Hubble constant. Current theories see this as a real movement, even though the recessional velocity is not a kinematic movement in the inertial frame of the receding galaxy. Let's take a closer look at these two galaxies. Current theories say that during the time that the light from the distant galaxy takes to reach us, the galaxy continues to move away. This is called the comoving distance. But in the fractal topology of space-time theory, there is no real movement, and instead both the galaxy and the eventual observer carry on shrinking. And a clue as to why we see the light that has travelled with time and not through time has a redshift is revealed in the way the travelling light spectrograph has not acquired any shrinkage. Therefore, it is we that are blue shifting as we displace cosmic time ever faster while our proper time passes slower. There is still a redshift distance relationship, and we can still deduce this from the apparent recessional velocity figure for the Hubble constant, but there is no need to correct for any comoving distance effects. This simple formula will give us a distance relative to our time dilation in regards to the apparent recessional velocity. We're going to a much larger scale now. Imagine this diagram is about 10,000 megaparsec across. If we are in the middle, even if we could travel at the speed of light, it would be impossible to reach some of these galaxies, no matter how much time we had, because at this distance the recessional velocity exceeds the speed of light. The interface between the luminal and superluminal we call the Hubble sphere. Although the measurement of this distance is unchanging, the Hubble sphere shrinks along with our measuring rods. Note the galaxy with the arrow. Watch how the apparent recessional velocity gets faster and faster. The greater the distance to a galaxy, the greater the observed light has been shifted towards the red end of the spectrum, and so we can use the redshift Z number as a distance increment, which is ideal for very large cosmological distances. And because there is no comoving positional change, any peculiar movement will be relatively local, forming clusters and galaxy mergers. In this theory, the Hubble sphere is 4.3 thousand megaparsec, which is Z1, and the visible horizon is a whopping Z 1100. An observer sees the distant galaxies as they were back when the light we see left, so at great distances they should look larger than what we would expect from just the perspective, although relative to the inertial frame no galaxy is actually moving, but just like time dilation is a real effect, the shrinking light speed ruler effect makes the apparent recessional velocity also real in a relative way. So the superluminal Hubble sphere is an event horizon that we could never reach. You may then wonder how it is that we can see beyond it, and we can. In this theory, the Hubble sphere is a limit to the future influence of light leaving the observer. We can see the more distant galaxies because their light is reaching us from the past. We are inside their Hubble sphere. We are inside the Hubble sphere of all things that we can see, including the light from the very first glowing matter, that is, the cosmic microwave background radiation. How big an object looks depends on how far away it is due to perspective. And when we look at the angular diameter of a galaxy, one would expect on average that the further away it is, the smaller it will appear. You might imagine a graph like this, where we have the size in arc seconds on the left and the distance on the bottom corresponding to the redshift z, to look something like this. But when we observe these very distant galaxies, we get this, where galaxies appear to gain size with distance. Now either the galaxies are undergoing a significant and unexplained process in their evolution, or there is a significant lensing effect due to the expansion of space, or, as the fractal topology of space-time theory predicts, the galaxies were actually much bigger in the past, and the redshift to distance scale so much larger than in the standard model. This ruler represents the look-back time according to the standard Big Bang model. Each centimetre represents a billion light years, and this represents the Big Bang moment when time equals 0. Z1 is halfway back, nearly, and the Hubble sphere would be over here. The furthest galaxy so far detected would be here. Note how very close it is, comparatively, to the cosmic microwave background radiation. In the fractal topology of space-time theory, the Hubble sphere is at Z1, and as far away as the particle horizon would be in the Big Bang model. But for the fractal topology of space-time, we have to change the scale of this ruler to make any sense. And now the Hubble sphere will be inside this little donut, and the cosmic microwave background radiation would be over 1,000 times further away. The particle horizon will be at z equals infinity, and the Big Bang or Genesis moment would be at an infinite time and distance in the past. With the extra time and distance indicated by this theory, there is plenty of time for the most distant galaxy detected to have evolved. In my diagrams, the galaxies are shrinking with the matter. This is due to gravity we do not normally account for because it is hidden. To explain, I will take you back to our imaginary space elevator. The measured orbital distance remains the same. Yet over time, the Earth and the elevator are shrinking, and therefore, relative to the past, the elevator and any satellites have moved a fraction closer to the Earth. This is a real but hidden peculiar movement towards the Earth. The cable of the space elevator stays taut due to the weight higher up. If we were to descend the elevator a bit and drop these two items, they would slowly start to fall. The effect is started by that tiny hidden peculiar movement. It need only be a fraction of an atom, but that starts a feedback loop with the distance asymmetry relative to the position and the speed of light. Falling like these items, you do not feel the Earth pull you down. You would instead feel stationary, and the cable would appear to be moving past ever faster. It is your future distance disappearing, and so you feel nothing till you hit that thin blue line we call the atmosphere. Back here on Earth, the distance to the centre is still disappearing, but the ground stops you getting any faster. So the chair here is not pushing Alice up, it is Alice being perpetually decelerated by the chair. This hidden, peculiar movement that initiates the gravity effect locally towards the centre of mass is extended to all gravity-bound objects like stars in a galaxy, galaxy mergers, and the formation of galactic clusters. The opposite effect will be noticed in the voids between galaxy clusters. Gravity is still positive there, but decreasing due to the hidden peculiar movement of galaxies as they migrate away from the voids and towards a gravitational focus point. Bentley's paradox is not so much solved, but is eked out to the end of transfinite time. Examining the Coma galaxy cluster, the missing mass or dark matter was first inferred by the maverick astronomer Fritz Zwicky in 1933. His work was largely overlooked by the then elite, of whom he said seemed free to appropriate discoveries and inventions, and referred to those individuals as spherical bastards, because they are bastards whichever way you look at them. The problem was rediscovered by Vera Rubin in the 1970s, not the legitimacy of the so-called elite, but the missing mass, when she noticed something odd about the rotation of the stars in the galaxies. The stars should rotate like this and simulate the way planets orbit in our solar system. But instead what we find is a much flatter rotation curve with the stars rotating almost as if fixed to a giant wheel. But if we were to consider time getting slower monotonically towards the supermassive black hole in the centre of our galaxy, then that gives us a shrinking ruler effect that will keep all the stars at a self-similar orbital distance to each other, producing the absurd flat rotational curve. So a spiral galaxy, where space-time is fractal, is similar to a squashed Euclidean 3D tin can. How fast we are shrinking is opposite to the expansion, so scale down the volume of space with a radius of 1 megaparsec to the volume of the Earth with a mere radius of 6,371 kilometers, and then the 70 kilometers per second becomes 0.46 millimeters per year. So the Earth's diameter will be relatively smaller year on year by about a millimeter, all unnoticeable and unmeasurable to the occupants. So going backwards in time no longer gives us a shrinking space or a positional change for the galaxies like this. There is not just one primordial atom with almost infinite density, for that would be the mother of all black holes, surely. With the help of vector here, we can see that the buttons shrink, not the balloon. When we rewind time in this theory, the galaxies get bigger and eventually lead back to our universe full of hot plasma. That has always been on the visible horizon and has now cooled to become the cosmic microwave background radiation. I like to imagine that the early atoms were so big that nearly all space was inside them, and so the mean mass density of the universe has always remained the same. Going back in time, atoms get bigger, less dense, but have the same mass. So the initial universe was just opposite to that mother of all black holes. The temperature variation of the cosmic microwave background is at the most plus or minus 4,000th of a degree centigrade, yet different regions of the horizon could not have been in thermal contact with each other due to the great distances, which should not be possible, not with a finite speed of heat transfer, even at the speed of light. This was first noticed by Charles Meissner in the late 60s. This is called the horizon problem. Although the distances are far greater in the fractal topology of spacetime theory, the energy that created the matter emerged everywhere at once under identical initial conditions, and so my party girl was infinitely big and hot right from the start. We could also consider that our light speed measuring rods were longer as we go back in time, and so the speed of light would therefore be infinitely fast at the birth of our universe, and so our infinite universe would have been in thermal contact everywhere simultaneously at its birth. With current theories, there are three possibilities for the evolution of the universe. With the expansion as a constant, much depends on the average density of the universe. Too high, and acting as a brake, the expansion will go into reverse. The universe heats up again as the matter heads back towards the big crunch. Just right, and the universe expands forever, and this is what the Wilkinson microwave anisotropy probe data is showing us. If this is the case, it is quite remarkable after all this time. It has been compared to balancing a pencil on its point at the beginning of time, and it's still standing there now. If it is too low, then the universe is open, and we head for the big freeze with no end. Parallel lines diverge in a strange hyperbolic space geometry. In this model, space does not expand. The average density is as it has always been since the Genesis moment. All matter is shrinking relative to absolute space, but mass remains the same as we measure distances relative to our shrinkage. Space is flat on a large scale and over time. At the Genesis moment, matter has no immediate inertial movement from any explosion. With no push involved with the apparent expansion, the pencil analogy would be that it is dangling from a thread and very stable indeed. This is how the current theories see evolutionary age of the universe. The cosmological principle assumes that the universe is homogeneous and isotropic viewed from a large enough scale, and so everything here looks the same with accelerated expansion. All the universe looks younger, less developed here. Things start to become visible here, and everything is in the process of cosmic inflation here. But the expansion over time does not adhere to the cosmological principle. If it did, this graph would look more like this. So when we look at the expansion as a changing distance scale with space remaining absolute, even the time narrative of the universe becomes homogeneous and isotropic. This model adheres to what cosmologists call a perfect cosmological principle. We see fractal patterns everywhere, clouds, ferns, snowflakes, etc. And with mathematics we can create natural-looking special effects scenes for films, or create beautiful dynamic patterns. But what I really want to demonstrate is how fractals are at the very heart of space and time. Back here on Earth, life often forms fractal patterns, like this tree fern. Each frond contains many self-similar smaller copies of itself that we call levels of description. So this would be the first level of description, this the second, and then the third, and so on and so forth. When stacked like this, they become a nested set. The progression is known as the fractal depth, with the lowest level called the fractal prime, in this case the fourth level being the leaflet. When we look at the evolution of matter, we see a similar hierarchical nested set, from the infinite plasma, then infinitely many population 3 stars that form from pristine gas clouds, and then the latter stars to form as smaller and more dense, and finally we get to the very compact objects like white dwarf stars, neutron stars, or even black holes. Time slows down over time as matter shrinks, until matter becomes or enters a black hole. A black hole experiences no elapsed time, while elsewhere proper time marches on, because they have an existence in cosmic time while proper time passes infinitely slowly there. At the Big Bang or Genesis moment, we must have emerged from an opposite type of singularity to a black hole, where time begins infinitely fast, sometimes called the Whitehall singularity. If time can start and time can end, then any notion of a before or after time would have to be a timeless continuum, or a Big Bang or Genesis moment that never stopped. Every moment in time, a new infinite part of the universe emerges from the continuum singularity. Although I prefer the term eon of time, it is probably best understood if I call them other universes. We called galaxies island universes back in 1917. But these universes are infinite in their own right, each separated by their own infinity, and each being one of infinitely many parts of a nested ordered set, each having identical initial conditions and evolving over transfinite time. Both the white hole and the black hole are described as singularities, but what if, as the name singularity implies, they are in fact one and the same, where black holes lead everything back to the singularity, but only after everything in their universe has reached their fractal prime, a fractionalized big crunch that occurs at infinitely many positions in space, yet the same moment in time, a singularity of two opposites that unite as the one singularity. So we have not exploded into existence as a one-off event. We are part of a continuum. Each red disk represents the space of an infinite universe, and the clocks represent infinite evanescing matter and time within. The singularity is like the engine driving the universe like a magnetic core. But magnetic fields are not lopsided like this. The lines of magnetism have a symmetrical parity, like this. At the genesis moment, an equal amount of matter and antimatter should have emerged, and in this theory it does, but as entangled opposites separated at birth by their infinity, conserving the symmetry and charge parity. A natural assumption, but one I think not rationally afforded by current theories. So at the genesis moment, every matter universe has an entangled antimatter universe, both infinite and thus separated until they recombine at the singularity. We should also make this analogy three-dimensional and complete the field with this complex torus and have infinitely many universes emerging at every moment in time, filling the longitude lines and growing the latitude lines on this complex torus. If, out of all these universes, we are this one, then we share the same genesis moment with infinitely many this way and infinitely many this way. And so the universe diagrammatically opposite would be our entangled antimatter doubleganger. Every universe will have an entangled antimatter opposite. We can also make this supersymmetrical by making the analogy include the other dimensions. Dark energy. Our shrinking rulers produce a fictitious movement that has no real positional change and no energy needed to invoke it. Dark matter, explained by a combination of a hidden peculiar movement of gravity-bound objects and a fractal topology where the distance scale changes towards the gravitational focus point. For example, the supermassive black hole, giving a spiral galaxy the property of a squashed Euclidean tin can. The horizon problem. Going back in time, the universe emerges everywhere at the same initial temperature, and so the cosmic microwave background radiation should be at an even temperature, and it is now within 1/4000th of a degree centigrade. More time needed for observed levels of evolution. On this look-back time ruler, Big Bang happens here, at 1.4 millimeters or 14 billion years ago, and the visible horizon this wide at 46 billion light years. But in the fractal topology of space-time, the cosmic microwave background is this far away, at 15,500 billion light years. So there is time enough to form the most distant galaxy so far observed, and the largest of structures in the universe to form. The theory explains why the angular diameter of very distant galaxies appear to grow with distance. Missing antimatter. The first layer of time creates a fractal loop. No longer have we got the ultimate free lunch, with everything from nothing, for at the Big Bang or Genesis moment we emerge from a pre-existing time continuum where matter and antimatter are separated at birth. Gravity is another self-similar fractal loop where increasing time dilation feeds the distance asymmetry fractal loop where we keep falling even when standing still on planet Earth. Planet Earth keeps perpetually slowing us down. But I think most importantly, time is a parameter of change, causally self-reflexive, bringing absolute chronological ordinality to our beautiful chaotic fractal universe. As an amateur, I have no doubt made mistakes, but to know how the universe works, one has to first imagine, given the evidence, how it can work. Michelson and Morley did not find their ether, but they were instrumental in the discovery of a deeper question.